Hi everyone, welcome to our talk about avoiding unnecessary object creation. I'm Kathleen. I work at Microsoft on the Edge browser. This is my first C++ conference and my first time presenting, so I'm really excited to be here. This is my colleague Chandra.
Hey, I'm Chandra. Yeah, I'm a colleague of Kathleen from Microsoft. I've been programming in C++ on and off for more than 20 years. This is my second time attending C++ now, first time as a presenter, so grateful for the opportunity and really excited to be here.
Okay, so here are the topics we're going to be covering. First, an introduction about what extra objects are and why they're a problem, basic strategies to avoid them, strategies for string and vector, and then other common SDL types, associative containers using transparent comparators, and then finally moving data to compile time. If you have any questions throughout the presentation, please make note of the slide number. Should be a number on each slide, and we can come back to them at the end. We also have some candy on the side, so at the end, feel free to take any. Okay. First, let's go over what we're considering to be extra objects. So let's look at this code. When we're creating a string hello world, creating a copy of the string, str2, and then outputting the string. Since our goal was just to output the string, we could have instead just written this. In this case, we don't need str or str2. Even if we compile the code snippets with an optimization flag, the second example generates much fewer lines of code. In this presentation, we're considering extra objects to be objects that aren't necessary to achieve our goals. Of course, not all scenarios we're going to go through are as obvious as this example. Some background on the motivation for this talk. We work on a Chromium C++ project with more than 100 engineers. Over the past 5 years, while reviewing many pull requests, we've noticed certain patterns where extra objects are created. This talk summarizes some of the most common examples and patterns and is geared towards being guidelines to follow rather than going into depth about why exactly extra objects are created. Why are extra objects an issue? C++ is a value semantic language by default, which means assignment copies the value. In this example, C and C1 are different objects. The second line calls the copy constructor to create a new object. Let's assume the copy constructor has been defined for my class. We'll be using this code to log when operator new and delete are called in our examples. It prints when the objects are created or destroyed. For example, we have this code that creates a string s and assigns s to a new string s1. This is the output showing when each string is created and destroyed. Here we can see the copy constructor string is called when creating s1, and then operator new was called to allocate memory. Allocating memory is a costly runtime operation, so avoiding that is beneficial. Let's look at move now. This is using the move constructor to create a new object. In this code, we use move instead of assigning s to s1. You can see operator new is only printed once and is not logged when move is called. The move constructor of string does not allocate memory, but instead swaps memory. Even though move creates a new object, it's not costly at runtime. So we've looked at copying and moving, but we'll try to improve on that. In this code snippet, string s is assigned to the return value of getStr, which returns a string. Only one string is created and destroyed. This is in-place construction, and no extra objects are being created. Our goal is to create objects in place. If we can't do that, then move is preferable over copying the object. Let's take a look at extra objects with vectors now. In this code, we create a vector v, which contains 6 ints. Another vector v1 is created from v. We can see 2 vectors are created here. Vector's copy constructor is costly for runtime since it allocates memory. If we compare it to move, no memory was allocated for v1. Now let's look at list. This example is similar. List L is created and L1 is created as a copy of L. Operator new is logged 3 times, once for each element being added to the list. List copy constructor is even more expensive than vector. If we instead use move to create the list, we can see new is only called 3 times to create the original list and is not called to copy the list. Using move is better because it didn't allocate memory. To summarize, extra objects are a problem because the object's creation can cause costly operations at runtime, like memory allocation. They can cause more code to be executed at runtime, and they can need more stack and heap space at runtime. So you might be wondering how much performance benefit you'll get if you remove all temporary objects. And our answer is, please measure your own scenario. It can really vary based on your code and what you're trying to optimize for. Sometimes it's okay to create extra objects, though. Some of the types are basic data types like int and float. Objects that are small in size and do non-costly operations in their constructors, like string view, span, initializer list, and range view types. Examples of costly operations are memory allocation, operating system calls, and running costly algorithms. We can consider objects that C++ SDL considers to be lightweight as a small object. For example, string view and span are 16 bytes in a 64-bit system, and MD span is 24 bytes. For our purposes, let's consider any user-defined types that don't have costly copy operations and are less than or equal to 24 bytes as a small object. We can use compiler warnings and clean tidy checks to detect when our code has some potential improvements to be made. Here are some clean tidy checks we'll be using to detect some of the examples we're going to go through. If you turn on WAll, it will catch many types of issues. Using extra will catch more, and everything will probably catch too many issues to be helpful. Right, and then I'll pass it off to Chandra.
Thank you, Kathleen. Let's move on to the next section, section 2 out of 7. This is basic strategies to avoid extra temporary objects. Okay, so we'll start off with the most common scenario, passing an argument to function. More specifically, passing a non-trivial type as a read-only argument to function. What do we mean by that? So let's look at some code. So here is us having a function foo, which takes a truth string as an argument by value. As you can see from the comment in the code, it just reads the string. It's not updating it, so hence read-only. Here's some code in main which exercises that. So what we do is that we set up a truth string over there. The string is big enough so that there is no small string optimization happening. We have some print statements, and then we're calling foo with the string. Okay, so how do we know that whether there is a copy happening over there? So we'll do it indirectly by overloading operator new and delete. This is good, but GCC, when you use W extra, comes up with a warning for this case. Can anyone tell me what that warning can be?
Maybe it's also overloading the same operator for debugging stuff? No?
Yeah, that's a good suggestion.
But that's not the answer.
No. Okay, let me give the answer. So what happened is that in C++ 14, they actually added more overloads to operator delete. So what they did was that, here you can see that operator delete has only one argument, void star. So they added overloads which have a second argument. So void star and size underscore t. So this is saying that, hey, you should also overload for that. So if that is present, then that will be called instead. Anyway, it's a harmless thing. So let's move on. Let's look at the output. So as you can see, that statement foo s, that actually shows an allocation and deallocation happening, meaning a temporary string was constructed over there. What do? It's better to use a const reference in this case. So we just change the type from a std string to a const std string reference. And here is the output. As you can see, temporary is gone. So guidance. As a rule of thumb, pass non-trivial read-only objects as const reference in arguments to functions. Note that the example was with truth string, but the principle applies to any type which has a costly copy operation. Now, string is special, so it has a special view-only type. So just for strings, in this case, you can also use a string view. And yeah, we do know string view has nuances. So we'll consider some of those in the later slides. Finally, to preempt a question, we also do know that const reference is not the most optimal in some cases, and we'll consider such cases later in the presentation. Okay, let's take the same example and run with the clang tidy check. So this one is called check performance unnecessary value param. Let's look at the output. As you can see, it rightly points out this issue. It says that, hey, you should make it a const reference. So it's a good check to have. Nice. We make the change. We use a string view instead. And yeah, the check passes as was expected, which is nice. What about our own types? So we create a type like this, struct B, simple type, and then create a function which takes B by value. And this also passes the check. Now, if I make a little modification, as you can see, I just moved that the copy constructor definition out of line. Once I do that, this check starts complaining again. Okay, why is that? Let's read a little bit of the documentation. It says that this check is only applied to parameters of types that are expensive to copy, which means they are not trivially copyable or have a non-trivial copy constructor or destructor. So that non-trivial copy constructor is the one that was flagged over here. So what is happening over here is that the moment we move that copy constructor out of line, it became a non-trivially copy constructible class. So that's why it is worrying. So yeah, beware of this kind of nuances of C++. So when in doubt, always stick to the one rule of one as close to as possible. Let the compiler generate all the special member functions for you, okay? And you know, this particular struct is a really bad struct. Can anyone tell me why is a bad struct? Okay, it's bad because it's not either copy assignable nor is it move assignable. The moment you default only the copy constructor move constructor, the other two, the assignment operators will be deleted. Okay, so that's why stick to the rule of zero as closely as possible. Okay, enough with this scenario. Let's move to the next scenario. Returning non-trivial member objects. For that, we have to create a super special struct. Yes, nothing special about it. But anyway, it will be our placeholder for non-trivial objects that we'll use for most of this presentation. Its superpower is printing. The print statements in its special member functions help us in understanding whether copies are being made. So if there is a copy construct being called, this is what we'll see. We don't like copies. So we'll try to see, can we actually convert that into a move? We'll try to do even better. Try to get an in-place construction. So as Kathleen mentioned, that we want in-place construction without copies or move. Okay, with that class mentioned over here, let's move on to the actual example. So for that, we'll create one more class, very simple class that has this A as a member. And then it has two functions. One A, which returns a const reference, the other A not create, which just returns A. Here is some code calling A not create. We just create my class and then call A not create. And here is some other code calling A. And here's the output. So as you can see, no object is created for the const reference return. Without the const reference, the copy constructor is called. So here's the guidance. When returning non-trivial member variable from member functions, consider returning as const reference. So let's take this example, which is supposed to be working correctly. This is the correct code to write, and then make a simple modification like this. So what did I do over here? Instead of holding that value as a reference, I'm just holding that value as auto. And here's the output. So as you can see, when the return type is not held as a const reference, the copy constructor is still called to create an extra object. So be aware of that scenario too. Okay, so let's take the same example and remove some print statements and then add a little bit more of a code. And then try out a new clang tidy check. Performance unnecessary copy initialization. Let's see what it says. So as you can see, it actually points out these two places in code which can be optimized. In both of these cases, you can actually use a const reference instead. So this is a good check to use. Okay, next scenario, range-based for loop. So for that, first of all, we'll create a vector, a function, getVec, which returns a vector of n elements of our type A. And with that, let's see some code. So This main function first calls getVec with 2 to create a vector of 2 elements of type A, and then runs 3 range-based for loops. So the first one with a const auto, second with a const auto reference, and the third with a forwarding reference. Here's the output. So as you can see, the const auto traversal creates extra objects. The other two lead to no temporary objects. So here's the guidance. Use const auto reference or forwarding reference in range-based for loop traversal for non-trivial object containers. So let's just take the same example and try out a warning. So this warning is known as range loop construct. This comes under the umbrella of WAL warnings in Clang. That's in the output. As you can see, it rightly points out this particular issue, which can be optimized, which can be converted to a const auto reference, which is great. Let's dig a little bit more into it. For that, we'll create a struct A, and this simple struct has 2 functions, foo, which is a const function, bar, which is a non-const function. Here's some code exercising that. So simple code, we just create a vector of string, it's empty, and then run a range-based for loop on top of it and just print the elements. Nothing will be printed because the string vector is empty. Then we create a vector of A, which is again empty, and then run 2 range-based for loops. The first one with the const auto, which in each iteration prints foo or calls foo. The other with autoway, which in each iteration calls bar. Here's the output with the range loop construct. As you can see that it rightly points out an issue, but it's also missing issues. So what do? So we try another Clang tidy check. Performance for range copy. And here is some code. Here's the output. As you can see that it does flag that particular problem. Okay, I think it's just too light for you guys to see, okay? So it's actually flagging the first vector over there, that auto v vec. So that one is being flagged. Do you have any questions on that? Like, because I can see it in my slide, but I can see it over there. So it's the first loop that is being flagged. Okay, so then the question is that, what about the last loop? The one that calls bar? Why is it? Yeah, go ahead.
It's calling a non-const function.
Exactly, that's awesome, yeah. So the last one is not actually being flagged because it's calling a non-const function over there. So it leaves it up to the developer's discretion to use a reference in that particular case. That's interesting. Okay, you see that I created that struct and have a str as a member variable, but never actually used it in the slide. So yeah, it's a side bug. Or is it? Do you think it's a bug or a feature that string variable is a member variable of struct A? Okay, so it's actually a feature. So what is happening over here is that if you remove that string from the member as a member variable, the struct A becomes a trivially copy constructible struct. And for trivially copy constructible structs, it's just totally fine to actually use them as a by value in the range-based for loop. So the moment we added that string inside the struct A, it became a non-trivially copy constructible. Hence, this check started flagging. So though it was not used in the examples, but it is necessary to show these examples. Okay, next scenario, structured binding. So for that, we'll create a simple struct B, which actually has a member, our struct A as a member. And here is some code. Both of these pieces of code do structured binding. The first one uses const auto, second one uses const auto reference. Here's the output. So as you can see, if you're not holding as a reference, the auto actually creates extra objects. If you do a const auto reference, there are no extra objects. So here's the guidance. Consider using const reference for read-only structured binding variables. Okay, next scenario. Explicitly moving objects out of function. What do you mean by that? So here's some piece of code. The function foo creates an object of type A and then calls toMove A in return. Here's some alternate piece of code which just does a return of A. And here's the output. So as you can see, the first one calls a move and the other one gets an in-place construction. So what is happening over here is that the explicit call to toMove defeats the named return value optimization. So yeah, don't use stood move in such cases. Now note, inner view is not required by standard, but most compilers implement it for such scenarios. Here's an alternate piece of code. This one also gets you in-place construction. However, this is guaranteed. This is guaranteed copy elision from C++ 17. Can anyone tell me, like, what is it also known as more technically? Okay, I hope I'm able to pronounce this properly, okay? There are two of them. One is deferred temporary materialization, and also it's called unmaterialized value passing. Okay, let's take this same example and then run it with this particular warning, pessimizing move. So this also comes under the umbrella of WAL checks. Yeah, and as you can see, it rightly points out this particular issue. So yeah, consider using this for your code. Now here we've talked about, okay, you should not explicitly move out of function. In some cases, you need to. So again, we have the same struct. We have this function foo, which does a structured binding, creates that object of type B, and then does a structured binding and gets that A as a reference and then returns it. Here's an alternate piece of code, does the same thing, only difference, just at a stood move at the end. Here's the output. So as you can see that without explicit stood move, the copy constructor gets called in this scenario. So if your copy constructor is expensive, you should do a stood move in this particular scenario. So there is nothing special about structured binding. This just applies to anytime you want to return a member variable of a local type from a function, okay? So as you can see, this piece of code, the first one just returns a return b.a, and the second one does a move, and here's the output. So as you can see that without explicit stood move, copy constructor gets called in this scenario. Okay, moving on, next scenario, lambda captures. Okay, here's some piece of code, very simple code. We just create an object of type A, and then first of all, we create a lambda, and then capture by value. And later down, we do that auto fn2 equals to fn, which means that we are copying that lambda. Here's a very similar piece of code. Only difference, instead of capturing by value, we are capturing by reference. Let's look at the output. So as you can see, when we are capturing by value, we are getting copies. So the moment the lambda is created, then the capture is taken as a copy. So that's why you see the first copy constructor firing. And then when the lambda is copied, the captured object inside it is also copied, which means that's why you see the second copy constructor firing. Whereas if you do the reference, there is no copies. So the guidance is, if it is safe to do so, like in this case, capture by reference to avoid copies. Okay, we'll look at one more scenario with lambda. So for that, we'll make some updates to our class itself and add some member variables which will return lambda. So let me remove some clutter over here. So there are 4 different functions. The first one captures by star this, second one this, third one by reference, and finally by value. And there is this code in main which calls each of those functions and then calls the returned lambdas. And here's the output. So as you can see, it's only the star this that makes the copy. Now, star this is supposed to make the copy, but just ensure that you really want to have the copy, okay? Okay, we are not yet done with lambdas. Oh, so sorry, let me go over. Now, in the last example, let me just go back. In this example, as you can see, we did the capture, but we actually never used a captured variable within the body of the lambda, right? So what if we do that? What if we capture the member variable in the body of the lambda, right? So here, what we're doing is that we actually added an int a as a member to the class. And in each of these functions, it's trying to print a, okay? And expectedly, this code does not compile. So this is the portion that is getting flagged, okay? And for good reason. The reason is that implicit capture of this via equal to was deprecated in C++20, okay? So this will not work. Okay, I think our final scenario with lambda, why was
it deprecated?
Yeah, because it's a little bit confusing actually. So they said that you better just use this explicitly. It's not super obvious. Okay, final scenario with lambda is varied captures. So there are 5 different functions. It's only the last 2 that are actually doing a varied capture by reference. Here is some piece of code in main, which is calling all the different functions, and here is the output. So as we can see, it's only the 2 functions which are capturing lambda by reference, which are capturing the variadic arguments by reference. Those are the only ones not doing a copy, the others are. So the guidance is that use reference capture with variadic arguments to remove the extra copies. Okay, handing it over to Kathleen for the next section.
Thank you. All right, so we'll take a look at some strategies for reducing temporary objects when using string and vector now. So we can use string view to stop creating strings at runtime. We have a function foo that takes a string by reference, and another function fooBetter that takes a string view argument. In this code, we create a string stir, which is created at runtime. We pass the string hello to foo, and it creates a temporary string. Each time we call fooBetter, no temporary string is created. And there's the output of each function call. String view can handle string, const char star, and const char star with length as arguments without needing to create different functions for each one. It also doesn't do any heap allocation. String view can also be used to create the string at compile time instead of runtime. If you want to learn more about string view, you can check out this presentation from our colleagues Jasmine and Prithvi at CppCon last year. In some cases, we can't use string view. If we have a function like fooPlatform here that expects a null terminated string, we can't pass this string as a string view because string view may not be null terminated. There's no C++ standard null terminated string view. Chromium has its own implementation of a null terminated string view type, which we can use in this case. Let's look at an example where we have struct A, and it takes ownership of the string passed into its constructor or passed into the function setStir. So these are sync scenarios. Instead of using string view here, we can follow this C++ core guideline for will move from parameters, pass by rvalue reference, and move the parameter. Here we've updated the code to follow this guideline. So again, looking at the original code, we can use the cling tidy check, modernize pass by value to detect the same case and improve the code to pass by value and use move. Right now, this check only identifies this case in constructors. It's better to follow the C++ core guidelines from the previous slide, but the cling tidy check suggestion is still an improvement. Our next scenario we'll look at is using an alternative to string operator plus. We have 3 strings that we're concatenating using the plus operator. You can see 2 temporary strings are created, and then a final 3rd string is created. So in all, 3 strings are allocated memory. So what if we can use a function that concatenates strings more efficiently? Here we have the same 3 strings to concatenate, but instead of using plus, we're using a function called myStirCat. You can see only 1 string is created instead of 3 strings from the previous example. Does anyone have any guesses about how myStirCat could be implemented? Yeah?
Probably it checks the string sizes and it allocates one once.
Yeah, right. So here's our definition of myStirCat. We're using reserve to ensure a single memory allocation for the concatenated string. Our definition of myStirCat is inspired by the absolStirCat implementation. We also have another variation of the function in the appendix of the slides that doesn't require an initializer list to be passed in. If a string is small enough, no memory is allocated on the heap because string data can be contained by the string object itself. Temporary strings are still created though. In this code, there are 3 small strings being concatenated using the plus operator. No strings are allocated or deleted, but temporary strings are still created. If we use myStirCat instead, no strings are allocated or deleted, and only 1 string is created. So myStirCat is still optimal in this case because it only creates 1 string. Plus is only optimal in the case where there's a single concatenation and either one of the parameters is a string. Now we'll look at how to use string view substir to remove possible memory allocation. We have a function remove scheme, which takes a const string reference, and another function remove scheme better, which takes a string view. Both of these functions return a substring using s.subster. So this code calls remove scheme and remove scheme better. We can see when calling remove scheme with the const string reference, a string is allocated, but when calling remove scheme better with the string view, no extra string is allocated. If we don't intend to modify the result of subster, we can use string view subster to avoid the extra memory allocation. We just need to make sure when string view is used, the underlying string memory is still valid. We used reserve to prevent extra objects when concatenating strings, and now let's see how reserve can help with vectors as well. In main, we're creating a vector of size 4. We use a for loop to emplace back 4 objects of type A. Operator new is called 3 times, first with size 4, then size 8, and then size 16 to resize the vector to hold the objects we're adding. The move constructor for each object is also called every time a new vector size is allocated to move the objects into the new vector. Let's compare to an example where we reserve the size of the vector before emplacing back objects. When we use reserve, operator new is only called once with the size of the vector we need, and the move constructor for A isn't called at all because no objects need to be moved. So reserve again here ensures there's a single allocation and no resizing is needed. There's also a clang tidy check you can use to catch this case in your code. If you have an emplace back in a loop, it will suggest you call reserve before the loop. We can also use span to prevent vector creation. Here we have 2 functions, foo and foo better. Foo takes a const vector reference and foo better takes a span. In this code, we create a C-style array and pass it into foo and foo better. Passing the C-style array into foo forces a vector creation. In the output, we can see calling foo created 3 temporary objects. Foo better created 0 temporary objects. Span allows functions to be used with C-style arrays without needing to create vectors. Using span also allows the function to work with other contiguous containers like vectors, arrays, and initializer lists. One thing to note is initializing the vector like this with the initializer list creates extra objects. We'll go over this case in some later slides. If we need a non-temporary object to be created, like in this case, we'll update A prior to calling pushback, it's better to use move. In the non-move example, the copy constructor is called, but when we use move, the move constructor is called. It's better to take ownership of the resources. Now we'll look at the no-except move constructor. This is the struct A definition we've been using, except we've removed no-except from the move constructor. When we emplace back items to the vector, the copy constructor is called during vector resizing and not the move constructor. Even though we have a move constructor defined, the copy constructor is still being called. If we add no-except back to the move constructor, and again, emplace back objects, we can see the move constructor is called instead, versus the copy constructor from the previous example. So it's better to have a no-except move constructor here to prevent copies. One thing to note is if the code is built with libcpp has no exceptions, the no except isn't needed, but it's still a good idea to add it. If we again remove no except, we'll see how clang tidy can help identify this case. When we use the clang tidy check performance no except move constructor, we'll see a warning that move constructor should be marked no except. Okay, and then I'll hand it off to Chandra again.
Thank you, Kathleen. Thank you, Kathleen. Let's move on to the section 4 out of 7, temporary objects in common HTML types and containers. So first type, initializer list. So this was the example that Kathleen actually pointed to. So here we are creating a vector of our type A using the initializer list constructor, and this is definitely not optimal. As you can see, 3 objects are getting created, and then they're getting copied into the vector. What do? We can reserve and emplace back. So with that, as you can see, we do get the emplace construction. So the guidance is that use this reserve emplace back paradigm. It removes the need for temporary objects and instead does in-place construction. I totally understand that there is a lot of boilerplate code being written over here. We do have some code in appendix which is using forward as tuple to remove some boilerplate. You can peruse it later. Also note, though we showed this only for vector, a lot of other container types in the library also have initializer list constructors. So you have to, they will also suffer the same consequences, and you have to apply similar techniques for those cases too. Okay, vector initialization is done. Let's move on to stud pair. Here is one way to create stud pair of a type A and A. This is definitely not optimal. It's calling the copy constructor. So what can we do? We can actually call make pair. Make pair, what it does is it converts the copies into move. We can also use the class template argument deduction, which gives us the same result. So how do we get in-place construction? We call the piecewise construct constructor in this way. We have to use forward as tuple. We have to write more code to get the reward of an in-place construction. Okay, next type, similar to pair, tuple. We create a tuple of a type A and A in the same manner as pair, and we get the same result. Copies are being made. Use make tuple to convert the copies into move. You can use the CTAD version also, does the same thing. So how do you get in-place construction? So we just call the piecewise constructor of tuple, right? Wrong. So there is no in-place construction for tuple. So a move instead of copy constructor is the best we can do. You can read more about this in this Stack Overflow post. Okay, before moving on, a quick show of hands. If you include the copy constructor and the move constructor, how many constructors are there in tuple? So show of hands, less than equal to 10. Okay, 10 to 15. 15 to 20? Are you just shy or are you just thinking?
I don't know.
We're invoking our Fifth Amendment right to keep our mouths shut. Sorry.
Okay. So, okay, 20 to 25. Really pushing it, right? Okay, 25 to 30? Okay, 30 to 35? My God, okay. I'll give the answer, it's 28. Yeah, so I think there are just too many constructors. Okay, moving on to the next type, stud optional. So here is us creating a stud optional for type A in this particular manner. So this is definitely not optimal because it's taking the object and making a move inside into the optional. So what we can do is that we can call make optional, which gives us an in-place construction. We can also call the in-place constructor, which also gives us an in-place construction. That make optional actually internally calls this in-place constructor. So the guidance is use in-place constructor or make optional to do in-place construction. So now in this particular case, we actually initialize the optional directly. What if we want to defer the creation, okay? So here is the scenario. Here we're creating the optional and letting it remain empty. Then after some time, we want to push in the value A, 1, 1 into it. And this is one way to do it. Here's the output. As you can see that this is not optimal. It's actually creating the object and moving it inside. So what can we do to do better? We can actually use in-place. Okay, so in-place in this case, as you can see from the output, gives us the in-place construction. So in-place is definitely better than assignment for this scenario with optional. However, in-place can also lead to extra objects. Okay, so here is the scenario. So we have that same optional. So first of all, we want to set value 1, 1 to it, A1, 1 to it. So we're calling the first in-place. Then we want to change that to A2, 2. We're calling the second in-place. So as you can see from the output, in-place destroys the current object before doing the in-place construction. So here it actually creates the extra object. But I think from my perspective, this may be fine because if you want to remove this extra object, you probably need to create an own specialized assignment operator for your class. Okay, so this may be fine. Okay, moving on to the next type, stud expected. So here's some code creating stud expected. The success type of expected is our type A, and this is one way to create it. Then we're calling that function foo in main. this is yet another way to create it, and this time we are using the in-place constructor of expected. Here's the output. So as you can see, the in-place constructor removes the temporary object. So the guidance is, for a non-trivial type being used in success type of stood expected, use the in-place constructor to create the object in place. Okay, related to expected, stood unexpected, which is the error type of stood expected. To show this example, we'll create another class, which is error. It's a very simple class which just prints in each of the special member functions so that we can see, okay, whether copies or moves are being made. Now, let's look at an example. So as you can see, this function unexpected is calling the unexpected constructor, but the return type is stood expected. And our error type is the error type of stood expected. Okay, so this is calling the unexpected constructor. Here is another way to do it. This is calling the in-place constructor of unexpected. We are not done. Here is yet another way to do it. And this one is calling the unexpect underscore t constructor of expected. So here's the output. So as you can see, the unexpect underscore t constructor removes the temporary object. So the guidance is that for a non-trivial type being used in error type of stood expected, use the unexpect underscore t constructor of expected to create the error object in place. Yeah, I had to practice this a few times, otherwise like I was just, this was becoming a tongue twister for me. Okay, next type, stood variant. So this is us creating a variant of our type A and int. This is one way to do it. This is another way to do it using the in-place type constructor. Yet another way to do it using the in-place index constructor. So here's the output. So as you can see, the in-place type or the in-place index constructor removes the temporary objects. So the guidance being, for a non-trivial type being used in variant, use the in-place type or the in-place index constructor to create the object in place. Now in this scenario, we just created the variant. What if we want to change the value type? So this is actually a variant of A and int. What if we want to change the value type? So that becomes our next scenario. So what do I mean by this? So here you can see that we are creating the variant int A, and that first line itself, since int is the first type, so the variant is actually created of type int with the value 0. And next we want to change that type to A with 1010. So this is one way to do it. This is another way to do it using in-place. And as you can see from the output, in-place gives us in-place construction. Okay, so it's better for changing the type of the variant. So that becomes our guidance, that for a non-trivial type being used in variant, use in-place to change the object type contained within the variant. Now this was changing the value type. What if we want to change the value of the existing type? So this becomes our next scenario. So what do we mean by that? So here's some code. So what it does is that first it creates a variant using the in-place type constructor, and the variant is actually A00. Now we want to change that value to A1010, and we are using assignment to do that. So the alternate way to do it is using in-place. As you can see, none give us our goal of getting in-place construction, but and as you can see, in-place calls the destructor of the object inside stood variant to always get called. However, it's not any less optimal than assignment in this scenario. So you can definitely use in-place for this scenario also. Okay, done with variant. Next, toArray. So here is us creating an array of our type A using toArray. Here's an alternate way to do the same thing. So as you can see, the advantage of toArray is that you have to type less. So you are just typing the type only once in toArray. Okay. In the next piece of code, you have to typing the type multiple times, and you also have to mention the number of elements. So that's why people use toArray many of the times, because of the ease of usage. However, it's not optimal. Okay. So as you can see, the objects are getting created and moved inside, which is not good for non-trivially copy constructible objects. So, but actually, yeah, it's not getting in-place construction, that's it. So, but the other one with more typing is more optimal. Now, obviously we can reduce some typing using the reduction guide in this way. So as you can see, it's less typing over here. So which brings us to a guidance. To create a stored array of non-trivial objects, consider using stored array constructor instead of toArray. Next scenario, adding elements to vector. So for that, we'll make some updates to our struct A. What we're doing is that we're just adding a member variable int to the struct, and then in each of the special member functions, we're just printing it out. So here is an example. So we are just creating an object and calling the copy constructor and the move constructor, and here is the output that we'll see in these cases. Okay, so with that said, let's proceed with the actual example. We have this main function, we're doing reserve and then calling pushback. Second example, reserve with mPlaceBack. As you can see from the output over here, for vector, mPlaceBack allows in-place construction. So yeah, please use mPlaceBack instead of pushback. So let's take the same example and this time run it with this client ID check, okay? Modernize use mPlace. And as you can see, client ID does point out this particular issue. So though this example was only for vector, this particular check works for other containers also. So this is a good check to have. Now, there are a lot of mPlace star functions available for various containers in standard library. Deck, forward, list, stack, queue, set. So whenever possible, when they're available, use those instead of the alternatives. Okay, handing it over to Kathleen now.
Thank you. Okay, so we've looked at many types of sequence containers, and now we'll take a look at more associative containers. First, we'll look at using mPlace with maps. Here we have a map M with key type string and value type int, and we're creating a key of string hello and setting the value to 10. This is creating the string and moving it into place. Now we'll look at maps with more user-defined types. In this example, we'll use our user-defined struct A as the key type and int as the value type. We create a map and assign key A10 to the value of 10. A temporary object is created and then moved into the map. If we instead use mPlace, we get in-place construction. In this case, the key is the non-trivial object. Now let's look at the case where the value is the non-trivial object. Here we have a map with key type int and value type A, and use the subscript operator to assign a key of int 10 to an instance of A initialized with 10. Does anyone know if there's an issue with this code? Will it compile? Okay. So it actually won't compile. Struct A needs a default constructor for the code to compile. So once we've added that, the code compiles and we can see it creates an object with the constructor that takes an int and another with the default constructor, and then it uses the move assignment operator and two objects are destroyed. Instead, if we use mPlace or try mPlace, the constructor is only called once and no temporary objects are created. So we can see mPlace does in-place construction even if the value is a non-trivial object. Try mPlace also does in-place construction for the value object. Let's take another look at when the non-trivial type is the key in the map and see if mPlace and try mPlace behave differently. We'll look at the basic case, not using mPlace first, where the key A10 is assigned a value of int 10. This creates A and moves an object. If we use mPlace instead, only one instance of A is created and destroyed, so no temporary objects are created. Now let's look at try mPlace. Does anyone have a guess of what the output will look like?
My guess is that it will do that 2 times, so it needs to create an object to compare it whether the place is available.
I don't know if it compares. Does it compare? Yeah.
You calculate the cache on the temporary object and then move it into the bucket.
Yeah, it does move it. Yeah. So it actually looks the same as the first example using the subscript operator. So it does move the object. So if the key is a non-trivial object, then only mPlace allows for in-place construction. There was a paper accepted for C++26 that adds support for try mPlace that will allow it to behave the same as mPlace in this scenario and do in-place construction. It also adds in-place construction for the subscript operator. Now let's look at how mPlace works for constructors with multiple arguments. we have a struct B that accepts 2 ints in its constructor. We'll use this in a map with key type B and value type B. We get a compilation error if we try to pass 4 ints in to try to create 2 instances of B, so we can't do that. Instead, we have to create 2 instances of B and then pass them in. This calls the constructor and move constructor for both instances of B. So let's see if we can do better than that. Here we'll use piecewise construct with forward as tuple. This only creates 2 instances of B. This approach using piecewise construct with the forward of tuple uses the piecewise constructor of pair and does in-place construction. If we use try in place, the key object gets created and moved, but the value object gets created in place. Therefore, it's still better to use piecewise construct in this case. Now let's look at when the key already exists in the map. Here we have a map where the key is an int and the value is of type A. We place a key 10 with the value of A initialized with 20, and then place another value A30 to the same key. There's also an example for try in place so we can compare it. So no extra objects are created, even after emplacing and try emplacing different values. For an existing key, the value type object was not created. However, this is not guaranteed by the emplace specification. Try emplace does guarantee this though. Next, to take a look at insert or assign, we'll use this struct to see when objects are created. This is very similar to what we've seen on previous slides, except this time it takes 2 ints and it's a template, so we can name 2 identical types, key and value. When we declare and instantiate objects, we can see when their constructors are called. Using these structs, we'll create a map with types key and value. Here we're seeing what happens if we try to insert and assign objects to the same key. So first, the key object K is created, then the value 2020 object gets created, then the key value pair gets created, which calls the copy constructor for key and the default constructor for value. Value 2020 is moved into value of the pair, which was inserted into the map. And then lastly, we assign value 3030 to value associated with key 1010 in the map. Let's compare it to what happens when we use insert or assign instead. So this is doing the same thing and assigning a different value to the same key. The difference is highlighted here. You can barely see it. Insert or assign moves the inserted value object instead of using assignment. If you have a function that does both insertion and assignment, it's better to use insert or assign instead of the subscript operator. Right, and then pass it off to Chandra.
Thank you, Kathleen. Section 6 out of 7, using transparent comparators to avoid extra objects. So this is applicable only to associative containers like set, map, unordered set, unordered map, etc. Okay, so we'll understand with examples. So let us first consider a set of string as the key. So we'll use operator new and this overridden operator new and delete to detect string creations. And we'll check the functions count, contains, and find. So these are the functions that we'll check. Okay, contains was added in C++ 20. Okay, so what are we doing over here? So we are just creating a set of strings named S, and then calling count, contains, and find using as argument a character array. So once we do that, we can see this. There are allocations happening, which means that each of these calls to count, contains, and find are creating the temporary strings. Okay, so this is the case. If instead we use a string, so as you can see, the temporaries are gone. Okay, so if we don't use a string, then the functions count, contains, and find will create temporary objects. And this applies also to constcaster. So in this example, we're seeing a C-style string array, but it applies to constcaster also. Great. So how do we fix it? Okay, just a little magic. Yeah. Use it. Gone. Okay, so temporaries are gone because we added that special thing stdless which is a std-less specialization for void. Okay, so that is the transparent comparator being used over here, and that removes these extra objects. If we use a std string instead of the char array, then also the same thing holds. Okay, there is no temporaries, but there were no temporaries with the std string in the first place. So here is our guidance. If you're creating a set with string as the key, consider converting it into this form so that you can get the benefit of transparent comparison. Okay, little bit into transparent comparators. So they allow comparisons to happen without the need to create temporary objects in certain scenarios. So they were added in standard library in C++14. We are actually seeing only, in all our examples, we'll see only 3 functions, count, contains, and find. However, they were added to other functions also. So essentially, like they were added to the other lookup functions like lower bound, upper bound, equal range. And in C++14, they were added only for map, set, multi-map, and multi-set. They were added in C++20 to unordered set, unordered map, and those unordered associative containers. Okay, so they are actually identified by this type def is transparent. So here is the code for that std-less void specification taken from libc++. So there is that type def is transparent, which is converting this into a transparent comparator. So we have seen a stud set of string. Let's move into stud map with string as the key. And again, we'll write the similar piece of code over here. We are creating a map, empty, and then calling count, contains, and find with a character array as an argument. And as you can see, temporaries are being created. The fix is very simple. Just add the transparent comparator. Okay. So that's it. It's fixed. Okay, so the guidance over here becomes, if you have a map with a string as the key, then convert it in this form so that you can get the benefits of transparent comparison. Next type, unordered set. This is what actually added in C++20. So we'll write the same piece of code over here. We're just creating an unordered set of strings, and then calling count, contains, and find with the character array. And once we do that, the temporary is getting created. Then how do we fix it? Yes, we'll go and use a transparent comparator. And you see the temporaries are gone. Okay, that equal to is supported by standard, but what is our mystery type myString hash? So it's very simple. It's a simple type, as you can see over there. That is transparent is needed, that using is transparent is needed to convert it into a transparent comparator. And we're also adding functions to kind of get hashes for const, caster, and string view. So those are necessary. So here's the guidance. If you have an unordered set of strings, then convert into this form to get the benefits of transparent comparison. Final type, unordered map with stud string as the key. Again, we'll write similar code, just create an unordered map. It's empty, then call count, contains, and find with a character as the argument. And we get the same output. The fix is very simple, similar fix. Just add the transparent comparators over there. So here's the guidance. So here is all the guidance together in the same page. So if you're having a set map, unordered set, unordered map, using string as the key, then consider transforming into this form. Though not mentioned here, this also applies to the multi-set, multi-map, and their variations, and even to the flat map, flat set, which were added in C++23. Okay, so we have seen transparent comparators for string, which is a standard type. What about user-defined type? So yes, we can do that too. So for that purpose, first of all, we need to enhance our type struct A. We just need to add a comparison operator over here. We are using the spaceship operator so that it can be used in stud set. What is the more technical name of spaceship operator? Okay, it's also known as the three-way comparison operator. Because that auto that is returns, it's not a bool.
What is it?
So it's actually either of the three types, like 3 or 4 types, I think. Strong ordering, weak ordering, partial ordering. I think these are the 3 types. So they actually, like, what happens is that they can be compared to like string comp. It returns -1, 0, and 1, right? So those types can be compared in that manner to kind of get the pool out of it. Okay, so with that said, let's move on to our first step, std set. So here we are creating a std set, and we'll again just only consider the count, contents, and find. So we're just creating a std set A, and we're just implicing 20 into it, and then calling count, contents, and find with 10, which is not A, okay? And as expected, we are seeing that temporary is getting created over there. So what do? I think the most logical thing next to do is to add the second parameter to that set, right? What will the second parameter be? Studless, right? So assume that we have added studless as the second parameter over there, okay? So in the set, it becomes A, studless. Show of hands. How many folks feel that it will solve the problem? Thank you. How many people feel that it will maintain the status quo, not solve the problem? Okay. And how many people feel that it will make it worse? Okay, so it actually makes it worse. Okay. There are more objects getting created. It's because we didn't do the right thing. Okay, so what we needed to do was that we wanted it to compare with an integer. So we needed to provide something so that it can compare with an integer, right? So that's why we're just adding this spaceship operator over here. So now with that done, oh my God. Sorry, wrong click. Okay, so with that done, so this is the code that was creating temporary extra objects, like even more than that with the studless. So if we make this change, with that change, as you can see that it's gone, okay? Now, I have to say that this section will become a little bit repetitive, but hopefully, the repetition will help us understand the concepts a little bit better. So we're done with stud set. Let's move on to the next thing, which is stud map. And here we're doing the same thing. We're just creating a map. We're just implicing a map of A and int, implicing 2020 into it, and then calling count, contents, and find with 10. And as expected, we are getting those extra temporaries getting created, right? And so how do you fix it? So once we have made those modifications to A, in this case, the moment you add a studless, it's just fixed. Okay. Okay, next type, unordered set. So for that, first of all, in order to use our type A in an unordered set as a key, we need to make changes. So these are the changes that we need to make. Okay, so we need to add an equality operator, and then we need to specialize our own hash function for our type A. With that done, let's say some code. We are just creating an unordered set, then implicing 20 into it, and then calling count, contents, and find with 10. And as expected, they are creating extra objects. Okay, so what do? We just add transparent comparators to it. As you can see, we have added those two comparators over there. The equal to is definitely a transparent comparator, and we added our hash specialization over there, right? But as you see, nothing changed. It's exactly the same. And the reason is that, again, we did not do the right thing. So these were the things that were needed, okay? So first of all, we needed to provide an equality operator with integer in our struct A, and then convert our specialization into a transparent comparator by adding that using is transparent equal to void inside the struct, and then also providing one hashing function for an integer. So once we have done all those changes, as you can see, the temporaries are gone. Yeah. So with these changes, the temporaries are gone, okay? Final type, unordered map. We are just creating the unordered map again like this, A and int. We're implicing 2020 into it, calling count, contents, and find with 10. Here's the output, as you can see. And since we have already made the changes to our structure and hash function, so in this case, it becomes very simple. Just do that, get the temporary objects are gone. Okay, handing it over to Kathleen.
Thank you. All right, so our last topic, moving data to compile time. In our previous examples, we were talking about how to create objects in place to prevent temporary objects from being created at runtime. Instead of creating the object at runtime, we can create them at compile time. Memory for compile time objects is constructed at compile time, which improves runtime performance. If we have local objects like this, like a const string or vector, the const means we can't modify them. So we can move them to compile time by making them static const expr string view or arrays instead. Let's look at global strings and vectors. If we build using flags global constructors and exit time destructors, we get these errors. This helps identify opportunities for moving global objects to compile time. So we can make them const expr string view and array instead and move them to compile time. Here are the global string and vector again. These global objects are created before main starts. One way we've seen people on our team try to defer global object creation in our codebase is to make them magic statics. So here we have a static const object being returned by reference from getStir and getVec. The clang flag exit time destructors will also point out magic statics. Magic statics fixes the global constructor issue from the previous slide, but not the exit time destructor error. Sometimes if we move const data structures to compile time, some changes to the usage may need to be made. For example, here we have a function getVec that returns a const vector reference. So it's returning a reference to a global array above. Instead, if we convert global array to a const expr array k-array, getVec will need to return a span instead. So the calling code will also have to change. We just looked at moving string and vector objects to compile time, but what if we have a user-defined data structure? Here we define a struct some class that contains 2 strings and an int. We have a const global vector containing objects of this struct, and a function that searches for a string in any of the objects in the vector. This code gets the compiler warning that declaration requires an exit time destructor and global destructor. Instead, if we make a new vector in getArray and return a reference to it, we don't get a warning. Now the function containStir calls getArray. Absol no destructor can also be used here to annotate this scenario. We can also change our struct to use string view instead of string and array instead of vector, so we can move our user-defined data to compile time using const expr. In our codebase at work, we've seen quite a few instances where we could convert user-defined data structures to compile time. Another scenario we can improve is concatenating strings. In this example, we have 2 const expr string views, and when we concatenate them at runtime, the result will always be the same. In this case, we can use a custom class myCompileTime string joiner, which we'll look at on the next slide to do compile time string concatenation. When we use this, we have a compile time string, concatenated string. The static assert is to show that this is indeed done at compile time. And this is the implementation of my compile time string joiner. It was copied from the Stack Overflow post. You can also create your own class like this for your own code base. Can we move set and map to compile time? There's no standard compliant way to do this. Chromium has defined fixed flat map and fixed flat set that can be used to create compile time set and map. Stewed flat map and flat set were added to C++23, and they will be made const expr in C++26. Once they are const expr, then some additional code can be written to create their instances at compile time. Until then, you can consider writing your own simple wrappers. We have some examples in the appendix if you want to take a look later. And that's all the topics we're covering today. So to recap the key points, we want to have in-place construction without copies or moves. To do this, we can pass non-trivial objects by reference, use view types like string view and span, use in-place constructors for SDL types, use mplace in containers, use transparent comparators, and move data to compile time if possible. And you can also use clean tidy checks and warnings to identify potential improvements. And thanks to the C++ community for all the great articles and videos that made this talk possible. And then, any questions?
So regarding the question that you had about implicit, regarding the question that you had about implicit triumphs, so the limitation that we saw over here, right, it comes from the signature of the functions. So if you look at implicit signature, right, it takes a variadic template. Okay, so that's why implicit can actually, if you have just pass in 2 arguments, it will totally create those out of it. And if you use that piecewise constructor, it can totally get an implicit construction. Triumph actually has different. So basically, it takes the first argument, which is exactly the key type. Okay, and the second becomes variadic. So because you have to get in that key type over there, so that's why we had to kind of do that explicit conversion over there.
So I was right for the wrong reasons.
Yeah, I guess so.
Another question, doesn't the compiler, when you have a variable and then I use std, so I have a variable and then I pass it as to a certain function, and then I don't use it anymore, doesn't it automatically generate std move there because that variable is out of scope?
Yeah, it depends on the type actually. So if your type is a non-trivial type, it will not do that.
Okay.
It will not do that. So, but if you can see through your type, right? So it's a trivial type, then it can do whatever it wants.
Because
like
let's say you have the variable and you imagine you have a function and there are 2 overloads. One is using a reference, and one is using by value. One is as you can use it with a forward reference, and then this variable you call the function. Now the compiler has 2 options, but you didn't specify std move, but the variable will be destroyed in the next step.
Yeah, but it will not do that. So I'll just say that probably you are probably just trying to mean, I think you're just trying to mean R value reference in this case, not the forwarding reference. So yeah, so by default, if you actually have a const reference and an R value reference, then by default, it will actually just go and pick the const reference unless you are returning a temporary. So basically, there are 2 ways it can actually pick the R value reference. So either you kind of do an explicit stored move, or you are returning a temporary. So you for example, if you have a foo which takes a string as an R value reference, so if you call foo with hello, it will call that function. Okay, or if you actually have a function get string that returns a string, then if you call foo with get string, it will actually call the R value reference. But if you actually have something like a string s and then call foo s, it will actually call the other one, the non-R value reference.
Even though it gets destroyed in the next.
Yeah, it doesn't matter.
Yeah. Okay.
Basically, it just function overloading rules at that point. Any other questions? Okay then. Thank you, folks.
Thanks for attending.
Thank you.
Don't forget to take